Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. So today we are going to review Chapter 5, which is Concurrency, Mutual Exclusion, and Synchronizations. Okay, so let's start. What are the learning outcomes for these chapters? Okay, so the first one is the basic concept. Okay, then we are discussing on hardware approach. Means that we are using a microprocessor instructions, and then we are using the software approach, which is semaphores, monitors, and message passing. Then we'll discuss on the classical problems in concurrency, which is the producer, consumer, readers, and writers. Okay, so let's see the first one on concurrency. So what is concurrencies? So as you can visualize here, okay, concurrency means that you are doing at the same time so many things. Okay, for example, you can see here there car number 1 here, car number 2 here, and even some motorcycle here, and also in this area. Okay, so you can think that this one like what you call those SMP or multi-core system. Okay, so you can see you have one, 2, 3, 4 cores. Okay, if you have only one core, okay, one core, then you only have this road. Okay, then everybody need to queue. Okay, so the advantage of concurrency is it can be faster. Okay, there is a benefit that it can be faster, but also it can have some other problem. For example, if you don't follow the rules, somebody might cut the lines suddenly and accident might happen. Okay, so this is the same case with the computer system. Okay, now let's see one by one the concept of concurrency. Okay, the first one is mutual exclusion. What is mutual exclusions? Mutual exclusion means that whenever you get hold of one resources, no other resources can no other process can get the resources. Okay, for example, in here, if this car is walking toward this line, no other car can take over the lines. Okay, because this is mutually exclusive for this car. Okay, or in this example, you have the cake here, you divide it into resources, and this is the process number 1, process number 2, and so on, and this is resource number 1, resource number 2. When you get hold of this cake, for example, person number 2, process number 2, then no other person can take this cake forcefully. So this is called mutual exclusion, and this is important. Okay, in for example, you have two programs P1 and P2. You are accessing the same resources, which is the printer. Okay, process 1, for example, the Microsoft Word. Process 2, for example, Excel. Okay, if you don't have mutual exclusion, what will happen? You print half page from Microsoft Word and half page from Excel. So you'll have not your intended output. Okay, so that's why whenever we have concurrency, you need to have the rules. Okay, like this one, you need to have the rules. Okay, you need to have a mutual exclusion. Okay, whenever one process get hold of one resources, no other process can take forcefully that resources. Okay. Okay, now let's see another concept of concurrency, which is the deadlock. What is deadlock? Deadlock means if you have two resources fighting for the same two processes fighting for the same resources. You have only one resources here. Person 1 said, give me the cake. No, person 2 said, no, give me the cake, I need the cake. Okay, so then you have deadlock. Okay, so and also another side effect of deadlock is starvation. Okay, so this is another side effect of deadlock is starvation. So for example, process number 3 also requires R1 and R2, but you can see from here, resource number 1 get hold by process number 2, resource number 2 get hold by process number 1. Okay, and process 1 said, give me R1, I need R1 to complete my task. No, process 2 said, no, give me R2. Okay, I need R2 to complete my task. And then the P3 will be starved. Okay, will be on the starvation status. Okay. Okay, another concept of concurrency is data race. Okay, in essence, this is we can think like this: loser takes all. Okay, so the last one that get hold of the resources will determine the outcome. Okay, so let's see here. So for example, you have put x equal to 0. What will happen here? If x plus plus coming first, then you will get x equal to 1. Okay, but remember that it is determined by the loser. Okay, so the loser will be the winner here. Okay, the loser will be the champion. Okay, so what you have here, print x, then you will have yeah, this is print x equal to 1. Okay, so if this is on the last one, okay, for example, if print x here and then x plus plus here, okay, and then this one will be the champions. Okay, so you'll have x equal to 1, okay, and never get printed. Okay, so whatever printed here, it will be equal to zeros. Okay, so this is the data race. Okay, the last one on the concurrency concept is the atomic operation. What is atomic operation? It means that you cannot divide. Okay, no division. You cannot divide. You cannot interrupt. Okay, you cannot interrupt. Okay, it will run into completion. Okay, so this is called atomic operations. So I hope you understand the concept: concurrency, mutual exclusion, deadlock, starvations, data race, and atomic operation. Okay, now let's see the next learning outcome, which is the hardware approach to the concurrencies. How to solve concurrency using hardware approach. So let's see now when you have a uniprocessor. Okay, so when you have a uniprocessor, what will happen? Okay, so you have process 1 and process 2. You will have here interleaving. Okay, you can have only here interleaving. Okay, so when you have, for example, round robin, you need to switch. Okay, for example, process 1 doing something here, and then you have here P1. Okay, continue. Okay, so doing IO here, for example. Okay, and then it switched to P2. It has not finished, and it switched to P2. Okay, what will happen? Like you are printing Microsoft Word, and suddenly you need to switch to Excel file for printing. Okay, for example, here P2 also want to print. Okay, in this case. Okay, so what you need to do for this unit process, you need to have interrupt disable. Okay, you need to have interrupt disable. Okay, so when you do the critical sections, critical section is the one that you need to have a mutual exclusion. So the critical section is to ensure you have a mutual exclusions. Okay, so what you need to do in the uniprocessor system, you disable interrupt, means that the process 1 cannot be interrupted. It will process 2 means cannot be interrupted, so it cannot use this printer. It will wait. Okay, because interrupt disable, so it will continue here printing. Okay, now after it's finished, of course, then P2 can get hold of the printer. Okay, remember that after you finish the critical section, you need to enable interrupts. Otherwise, no other process can use your your resources. Okay, interrupt disable is only working on uniprocessors. Okay, but on the multiprocessors, it doesn't work. Okay, so let me clean this one. Okay, so on uniprocessor, it doesn't work. So why is that? Okay, because the interrupt might be disabled here, disabled in this one. Okay, disable the interrupt. Okay, but this one still can read. Okay, this one is still enable interrupt. Okay, so the first solution does not work in the multiprocessor or multi-core system. Okay, because in multi-core system you can have overlapping. Okay, you can have overlapping. For example, you are using the printers. Okay, you disable the interrupt in here, but still enable in here. Okay, so you can get hold of this one. Okay, so what you need to do in the multiprocessor system, you need to put some lock here. Okay, you need to put some kind of lock in the main memory. Okay, so the keyword here is the main memory. Why is that? Because you can set the key here, which can be read and set. So this key can be read and set by CPU number 1 or CPU number 2. Okay, so it can be read by CPU number 1 and CPU number 2. So the processor design have some atomic operations, which is special machine instruction called exchange. Okay, basically what it do this one. Okay, So let's understand this program. So you have bold equal to 0. So your bold equal to 0 for the first time. Okay, bold is in the main memory, shared the global variables, and then you parallel begin. You run P1, P2 until Pn at the same time. Okay, so then you try to get hold of the key. Key I equal to key I means key number 1. Okay, for process number 1, key number 1. For process number 2, key number 2, and so on. So key 1 will check on the bold. Okay, if the bold is 0 means this is free. Okay, then you enter critical section, but after that don't forget to set it back to zeros, otherwise no other process can use. Okay, so similar like this. Okay, similar like this. Okay, and remember that you use special machine instruction, so this one cannot be interrupted. Okay, these two commands, okay, do and while here in C cannot be interrupted because you are using the special machine instruction, which is the atomic operation here. Okay, so I hope you understand. So if one get hold of the bolt, okay, then P2, the other process will wait until the bolt equal to 0, means the resources is free. Then you can use you can check again. Okay, you can check the memory. The keyword is in here. Okay, the memory. And the special machine instruction also working on uniprocessor. Okay, this one also can be work on uniprocessor. Okay, the same principle, then you can apply it here. Okay, you just put the lock here. Okay, instead of disabling interrupt, you just see the lock. All process will see the lock. Process 1, process 2 will see the lock. Okay, if this lock means the resources is used. If it is unlocked means you can use the resources. Okay, so let's move on. The previous one we are using the hardware concept. Now we are using the software approach, which we are using the semaphore, monitors, and message passing. Okay, so let's see here. The first one is the semaphore. Okay, suppose that you have this is process, this is resources, or you can think this is like in the library. Okay, and this is the carrel room or the reading room. Okay, this is the reading room. Okay, so what you have here, there are 4 persons and only 3 rooms. Okay, there are 4 persons and only 3 rooms, so you're competing for resources. Okay, so the semaphores means you are using some kind of flag. So you can see here, this is the semaphore. Okay, if you translate, you can translate this is help actually. Okay, so what will happen, P1 will see the flag. Okay, we'll see the flag. Okay, we'll see the flag. Okay, we'll see the flag, and then it can go anywhere. For example, it can go here. Okay, but remember, if you are here, then you need to change the flag. Okay, you need to change the flag here, like this one. For example, this means this is occupied. Okay, so the next person will see R1 and R2. Randomly they can choose. Okay, because there's no one to tell them which one, so they can use this one. Okay, this is the same reading room anyway, so you can choose, for example, R2, but don't forget that you need to change the flag to here, and so on. Okay, I hope you understand. Okay, so here when you put the lock on the doors, this is called, you are using the binary semaphore. Okay, only 1 and zeros. Okay, 0 and 1. Okay, 0 mean free, 1 is locked, for example. So this is 0, 1, 1. So R1 is free, R2, R3 is locked. Okay, so whenever you have some special condition, this is mutex semaphore. Mutex semaphore means only the process, only the person that locked this one can unlock the R3. Okay, so this is called mutex semaphore. Okay, only the process that lock the room, they can unlock the what you call the room. Okay, so this is called binary semaphore. Okay, the other type of semaphore is the other type of semaphore is general counting semaphore. Okay, so let's see here. Let's see. So the flag is not put on the room. Okay, but you have some special flag here, counting semaphore. So you have general semaphore. Okay, so this is general semaphore. So in other words, this is also counting semaphore. Okay, so it will count. Okay, So using same wait and same signal. Okay, same signal you are freeing, same wait mean you are waiting. Okay, so for example, in here I have 3, so the counting semaphore it will be 3 here. Okay, the first one equal to 3. Okay, then when person 1 is coming, okay, take any of the resources. Okay, any can be R1, R2 or R3 because this is the same resources, same type of resources. Okay, then it will flag like this. This is same weight. Then it will update to become 2. Okay, then the next one, okay, still have. Okay, then it will update this one 1. Okay, and the next one also the same, P3 here. Okay, it will update this is become 0. Okay, then when it goes to 0, you know that there's no more rooms. Okay, and the semaphore so can know whenever you go here, it need to wait, it will wait. Okay, so this is the principle of general counting semaphores. Okay, so the next one is the monitors. So normally you put what you call it has been implemented in Java. Okay, the language concept in Java. Now you have the middleman called the monitor, or you can think like managers. Okay, the same concept, but now you need to register here. P1 go to monitors. Again from here, then it will give you which room. Okay, R1 and R2 coming, give the room R2. P3 coming, give room. Sorry, this is R3. Okay, and so on. Okay, so then P4 when they try to come here, it's full. So the monitor said it is full. Okay, so it need to wait. Okay, so this has the advantage of simpler, easier to implement, but slower because of this bottleneck. Okay, so this is the monitor. The last one here is on message passing. Okay, so you have the same thing, R1, R2 and R3. Okay, you can think like you have some kind of liberal here, so you don't see the flag, but you need to create some kind of mailbox, or you can think this is like some kind of WhatsApp group. Okay, so you can whenever P1 want to use R1 for example, it will need to send a message to the mailbox, then it will broadcast to P2, P3 and P4. Okay, the same thing like when you send a message in the WhatsApp group or Telegram group, it will send a message to all the members. Okay, so P1 said I want to use R1 from 10 to 5 p.m. for example. Okay, then it will all other will receive the message, then it will know that R1 is taken. Okay, then as go around, then you can see you can exchange the message to book and free the resources. Okay, so this is the message passing. Okay, the principle of message passing is we have send and receive. Okay, so the last learning outcome for this chapter is the classical problems. Okay, so we have here producers, consumers. Okay, so what you have here, one or more producers are generating data or producing data and passing this in a buffer. A single or more consumer is taking items out of the buffer one at a time. So only one producer or consumer may access the buffer at any one time. So you need to what you can see here, you need to have mutual exclusions to the buffer. Okay, you need to have mutual exclusion to the buffer. Okay. Okay, so like this one, you have producers. You can have one or more. Okay, you have one consumer, so you can have one or more. So what producer do, it will produce this one. If one here, okay, then after produce, it go back here. Okay, then it can be taken out by the consumers. Okay, or you can also depends on the program. You can produce for example, then after that the consumer can take. For example, this is take by the consumer, so you only have buffer 1, 2, 3 and so on. So what you can see, for example here, when the producer produce in this buffer, the consumer cannot take this one until the producer has finished producing. Can you follow? Until the producer has finished producing the buffer, the consumer cannot take this one. Okay, after this is the producer finish producing the buffer, okay, then then the consumer can take this one. Okay, so you need to have a mutual exclusion on the buffer. Okay, so the other problem is on the readers and writers. So you can have any number of readers that can simultaneously read the file, okay, but only one writer at a time may write to the file. So and if a writer is writing to the file, no reader may read it, because it might have different value later on. Okay, so for example, you have here 6 file. Okay, so you have 6 file, and then you have readers and writers. Okay, the number of readers and writers can be varies. Okay, in our case here, for example, you have 3 readers and 2 writers. Okay, so when the writer get hold of here, no other readers or writers can get hold on this one. Okay, cannot access this file. Okay, but for reading maybe different. Okay, because reading does not change anything. So when the reader read here, this one also can be read by the other readers. Okay, so you need to have different treatment for writing and for reading. Okay, so for reading, whenever you get hold of one file or one buffer or one resources, then you need to have a mutual exclusions. Okay, so you need to have mutual exclusions, okay, to that buffer or file or resources. Okay, so I will run some simulation later on. I hope you can understand. I will add this one with the simulation, visualization simulation, okay, of this classical problem. But the principle is like this. Okay, you need to have mutual exclusion during producing and consuming. You need to have mutual exclusion when you are writing. Okay, so okay, that's for chapter 5. If you still don't get the idea, please let me know, and you can always ask in the Telegram group, in the mailing list, and the iTalim. Okay, so please take care and see you soon, inshallah.